Hey guys, how's it going? Welcome to day 45. I kind of want to answer the question I asked you at the end of yesterday's video about left-hand and right-hand Riemann sums being over or under estimates. We can tell pretty easily visually when we actually do them, but we don't want to have to always solve Riemann sums by graphing and drawing that thing. It just takes too long. So what I want to come up with is a way that we can determine whether or not we're going to have an overestimate or an underestimate when we're dealing with left and right Riemann sums. So let's take a look at what we have. Okay, it's going to depend on two things, whether we're over or underestimate. It's going to depend on whether or not the function is increasing or decreasing, and it's going to depend on whether or not we have a left Riemann sum or a right Riemann sum. So when we make our justifications, we're going to have to make sure we reference two things. So let's take a look at increasing functions first. Okay, so if we have an increasing function and we're doing a Riemann sum, let's say a left Riemann sum, very obvious here that I'm going to have an underestimate. So left Riemann sums will give us an underestimate when the function is increasing. Or if we have an increasing function with a right Riemann sum, we have an overestimate. But if we have a decreasing function, then the reverse is going to be true, right? If I have a decreasing function, now a left-hand Riemann sum is going to give us that overestimate. Whereas a decreasing function with a right Riemann sum will give us our underestimate. Okay, so as you can see here, a left Riemann sum could be an underestimate, right, or an overestimate. Depends on whether or not the function is increasing or decreasing. A right Riemann sum, same thing, could be an overestimate or an underestimate, depending on if the function is increasing or decreasing. So when we look at these in tables, I like to, right, they're going to tell you whether or not the function is increasing or decreasing. I just like to do a little quick sketch like that just to remind myself, is this an over or an underestimate? Because there's no rule about left always being under or over, right? Left and rights can both be over and underestimate. It depends on whether or not the function is increasing or decreasing. Okay, I want to talk about two more sums today, and then I want to look at solving these in table form, which is more common of what you'll see. The second sum, or the third sum that we're going to talk about is called a midpoint Riemann sum. Okay? And we'll talk about the advantages and disadvantages of a midpoint Riemann sum. Okay, so I'll draw a sketch kind of like yesterday's. Yeah, we have some function doing this. And again, we're using a Riemann sum, again, to approximate an integral. So we're going to try to approximate the integral from a to b of f of x dx. Okay, so let's put a somewhere and a b somewhere. Well, let's say this time we're using n equals 3 midpoint sums. Okay, so what I want to do is I want to divide this up into 3 equal partitions. So, got here and I've got here. I just need to put one about 1/3 of the way and another about 2/3. So again, yesterday we could have turned this into a left Riemann sum problem, right, by taking the left intersection of each rectangle, or we can do a right Riemann sum by using the right intersection point on each angle, on each rectangle. Midpoint does exactly what you think it means. It means we set the height of the rectangle at the f of x value in the middle of the two sides of the rectangle, right? So I'm going to look at this first rectangle. Instead of doing a point on the left or a point on the right, I'm going to use the middle point, right? Directly in between the two, and that's where I'm going to set my rectangle. And I'm going to color that in. And I'm going to use the middle point to make my rectangle. Color that in. I'm going to use the middle point to color it in. Now, when you look at this, I want you to think about what would be an advantage to doing a midpoint Riemann sum. Well, one advantage that you might see is the fact that if you notice on each rectangle, part of the rectangle is overcounting a little bit and part of it is undercounting. And if you notice, those two pieces tend to fit together pretty well. The nice thing about a midpoint Riemann sum is they tend to be much more accurate than a left Riemann sum or a right Riemann sum. So midpoint Riemann sums tend to be much more accurate. The thing that's hard about it is, I don't know, they're still not perfectly accurate, and I don't know if I'm too high or too low. I don't have a method for determining an underestimate or an overestimate. So that's how we do midpoint Riemann sums. And then again, if you're doing this, right, let's say, thinking of numbers, this was 1, 2, 3, 4. To figure out this value here, right, I'm going to plug in, since it's between 1 and 2 here, I'm going to plug in 1.5. I'm going to do f of 1.5 to figure it out. Here I would do f of 2.5. And this one I would do f of 3.5. Right? So I'm going to have to plug those things in, right, and just take the point that's in between the two boundary points. Okay, let's take a look at another form of sum, which is called a trapezoidal sum. The trapezoidal sum is different from the ones we've done because I'm no longer using rectangles. Anybody want to take a guess what shape I'm going to use? If you guess trapezoid, you are correct. right? We're gonna instead of using rectangles to shade in the area under the curve, we're gonna use trapezoids. So here's what this will look like. Again, I'm using this to estimate the integral from a to b of f of x dx. Using, let's say, n equals 3 again, trapezoids. So again, here's my f of x, the function f of x. Again, I'm going to turn it into 3. It's going to start out kind of the same way. I'm going to turn it into these 3 shapes. They look like exactly like we did before. But instead of using a rectangle, I'm going to use a trapezoid, and I'm going to connect the 2 endpoints. I'll use a different color here so it stands out. I'm going to connect here and here, and I'm just going to draw a line between them and find that area. I'm going to connect these 2 points and find that area. I'm going to connect these 2 points, find that area. Similar to midpoint Riemann sums, we tend to get much more accurate estimations, right? These estimations tend to be much closer, oftentimes, than a left Riemann sum or a right Riemann sum are. Okay? The nice thing about trapezoidal sums is if we know the concavity of the shape, we can also tell if we have an over or under estimate. So increasing or decreasing determines left or right Riemann sums being over or under estimates. Concavity determines whether trapezoidals are over or under estimates. So let's say this. Let's say we know f is concave up. So the second derivative is positive. That means f is concave up. Right? If we have a concave up graph, right, it's smiling. So if we put a trapezoid in there, right? If I put a trapezoid in here, because of the way it curves, I'm going to count this little region in here as an overestimate. Right? And I'm counting a little bit, this area, this region in here gets overcounted. So when we're concave up, our trapezoidal sum is an overestimate. If our function, however, is concave down, that would mean f double prime is less than 0. It would be kind of a frowny face like this. If I do a trapezoidal sum here, it's pretty easy to see that this is going to be an underestimate, right? So concave down, our trapezoidal sum is an underestimate. And again, you can always just, if you forget which one's which, you can always just sketch a concave up or concave down graph and draw a trapezoid in there, and you're going to see which one's over and which one's under. What the other difference here is when we calculate a trapezoidal sum, we have to use the area of a trapezoid formula. Okay? And what we're going to do, right, if I wanted the area of this, I'll go back up here. I want the area of this trapezoid. Okay? I'm going to take that base width here, and I have to multiply it by the average of the 2 heights, right? So this is like height 1, this is like height 2. I have to multiply by the average of the 2 heights. to solve that. Okay. So it's a little bit tougher to calculate, right? Especially without a calculator, but still very manageable. We average the two heights, and so we add them up and divide by 2, and then multiply by whatever the width of your region is. Okay, let's talk about solving some of these things via a table. So what I'm going to do here is I'm going to make a table. Okay. So here I have a table. And here's what I'm going to say. F of x is always increasing. And what I want to do now is, based off of this table of values, right, so I don't even know what the function is. I just know that the function is always increasing, right? I want to estimate the integral from -2 to 8 of f of x dx. Okay, so here's what it says. Estimate the integral from -2 to 8 of f of x dx using a left Riemann sum with n equals 5 equal subdivisions. Okay, so instead of, right, I could graph this thing out if I wanted to, and then do that left Riemann sum through the graph, but I can do it much quicker if I do it through the table. So here's what I'm doing. The first thing I want you to do, get in the habit of, is we want to start by rewriting our definite integral and then writing an approximately equal sign. These are estimates. So we want to show the grader that we understand its estimates by writing this first. So to start here, I'm going to say the integral from -2 to 8 of f of x dx approximately equals. So now the first thing I have to think about is, okay, how wide are my subdivisions? Well, remember that trick of b minus a over n, right? Let's figure out b minus a over n, since all of our subdivisions are equal. B minus a would be 8 minus -2 over n, which is 5, which would be 10 over 5, which would be 2. So our subdivisions each have a width of 2. What I like to do then is kind of annotate my table here. That means my first subdivision is going to go from -2 to 0, then from 0 to 2, then from 2 to 4, 4 to 6, and 6 to 8. And I count 1, 2, 3, 4, 5. They kind of look like staples on top. Those are my 5 subdivisions. Notice all the ones in the middle, right? Like if you look at the x value of 4, right? 4 is kind of the boundary for 2 different rectangles, right? There's a rectangle that's going to go from 2 to 4, and a rectangle that's going to go from 4 to 6. So if I'm using the left Riemann sum, okay, I know the width of each rectangle is a width of 2. right? The distance from -2 to 0 is a distance of 2. So I'm just going to calculate the area of all these rectangles. For my first rectangle, that's a width of 2, right? It's the difference between these two numbers. And since I'm using a left Riemann sum, I want to use the left height. Right? If you think about it on a graph, we'd start it from the left side. The left side of that region would be -2 with a height of 1. Okay? And I have to add together all the rest of these 5, right? I'm doing n equals 5. I should have 5 different rectangle areas. So my next rectangle goes from 0 to 2 on the x. Once again, that's a width of 2. Now, again, I want to use the left number, so I'm going to use 2 times 7. Plus, my next width is going to go from, so I did -2 to 0, 0 to 2. My next one is from 2 to 4. Again, that's a width of 2. And I'm going to use the left number 9. Plus, my next width is from 4 to 6. So that's a width of 2. And I'm going to use the left number of 11. And my last rectangle is from 6 to 8. Again, it's a width of 2. And I'm going to use the left number of 18. One thing you should notice here, since I have equal subdivisions, every single one of these numbers, right, 2 is a factor of all of them. So oftentimes we have to do this without a calculator. So instead of multiplying all those terms and then adding them up, one way you can make this easier is by factoring out that 2. And then you're left with 1 plus 7 plus 9 plus 11 plus 18. And then we just have to multiply once. All right, I'm going to do 1 plus 9 here is 10. 10 plus 7 is 17. 17 and 11 would be 28. 28 and 18 is 46. So this equals 2 times 46, which equals 92. So my left Riemann sum there gives me an answer of 92. Now, one question that you may be asked here is this an overestimate or an underestimate? Well, if we think about it, here's what we have. We know that f of x is increasing. So I just draw myself a little sketch over here and say, okay, increasing function, left Riemann sum. That's always going to be an underestimate because I'm not counting those areas right there. So I'd say this is an underestimate. To give a good justification here, I would say because I need to mention 2 things. I can't just say because I did a left Riemann sum, because left Riemann sums aren't always underestimates. I can't say just because the function is increasing, because increasing functions could have over or underestimates. But if I pair them together, it has to be true. So because f of x is increasing, and I did a left Riemann sum. All right, now if you notice, if you did a right Riemann sum instead, what would be different? Well, let's see what would be different here. If I did a right Riemann sum using n equals 5 sum intervals, all my widths would still be 2. So these numbers would all be the same. But instead of using the left number in each one, I would use the right number. So that instead of using a 1 here, I would have had a 7. I would have had a 9. I would have had an 11. I would have had an 18, and I would have had a 20. One thing that you should notice here, when we did a left Riemann sum, this number never got used. The 20 never got used. When I do a right Riemann sum, the 1 never got used. Okay? And obviously, I'm going to get a bigger number than 92 because every single number that I multiplied by got bigger. So, right, you can calculate it out on your own if you want, but I know it's going to make a number bigger than 92, and then my answer would be an overestimate because f of x is increasing and I did a right Riemann sum. Okay. Just 2 quick examples here before we go of tables. Okay, so here I have a function. By the way, when we have negative numbers, don't worry about them, right? Just multiply them like as negative numbers, and you'll be just fine. Okay, I want to talk about doing a trapezoidal sum here. I want you to estimate. We're going to go from 0 to 9 of f of x dx. Using n equals 3 trapezoids. Again, a quick b minus a over n. 9 minus 0 is 9 over 3 is 3. For each region spans 3, so my first one goes from 0 to 3, from 3 to 6, and from 6 to 9. But now I'm doing a trapezoidal sum. So I have to take the width times the average of the 2 heights. Okay, I have to take the width times the average of the 2 heights to estimate this. So let's look at what that would look like. Again, I'm going to start this off by writing my integral. Integral 0 to 9 of f of x dx. Approximately equals. Okay, well, let's look at my first trapezoid. What is its width? Well, its width is 3. But now I need to multiply by the average of the 2 heights. Well, I have to add up the 2 numbers and divide by 2. My next trapezoid will have a width of 3 again. And again, I got to average the 2 heights. And my last trapezoid is going to have a width of 3, and again, I'm going to average the 2 heights. Okay. Again, just make sure you have 3 total things here to match this number that's given here. Okay, so I know negative 3 plus 5 is 2. 2 divided by 2 is 1. 1 times 3 is 3. 5 plus 11 is 16. 16 divided by 2 is 8. 8 times 3 is 24. 11 plus 26. I'm sorry, I should have been a 15. 11 plus 15 is 26. 26 divided by 2 is 13. 13 times 3 is 39. So I just got to add these up. I'm going to do 39 plus 27. 9 plus 7 is 16. I get an answer of 66. Again, there's not enough information to determine whether or not this is an over or under estimate. Okay, I'm going to cut the video off there. We'll take a look at what midpoint Riemann sums look like in a table. Okay, it's very simple. The thing that you have to be aware of is that the regions always span over 3 total boxes, and instead of using the left or the right, you're going to use the middle number. All right, that's it for today. I'll talk to you guys later. 2 chains, bye.